So, the final bit with regards to the very last topic with regards to MOSFETs is with regards to characterizing MOSFETs. So, I felt that this would be a very useful module to have, which is the characterization of MOSFETs, because in most of your since this course is being offered to students from various disciplines, it is very likely that you are probably making MOSFETs, you are fabricating MOSFETs using new materials or new process techniques, etc. And in order for you to characterize these MOSFETs, we have gone through several ideas through this course, but I do not think it is quite obvious as to how to use those ideas to characterize MOSFETs. Okay. So, these few slides will just give you some insights as to what you might need to look out for when you have built a MOSFET, and what you might want to test for after you have built a MOSFET, so that it gives you some very elementary picture on some very useful or important parameters of the MOSFET that you could use for your research or for modeling. So, essentially let us say you have made a MOSFET. Okay. The very first characterization technique is the most essential, which is using your IV and CV information to extract key parameters of the MOSFET. So, what is the point of parameter extraction? So, if we want to extract parameters, right, and we want to extract parameters via experiments. And what is the point of extracting parameters by experiments, and what are these parameters? So, ideally the point of parameter extraction is to be able to define your current voltage characteristics in static and in dynamic, that is low frequency and high frequency characteristics of a MOSFET as accurately as possible. Okay. And we essentially want to identify all these parameters, mu, Cox, W over L, Vt, so that we can then start writing equations for the MOSFET and start defining the behavior of the MOSFET. Now, after we have built a MOSFET, what are the experiments that need to be performed in order to extract these parameters and start using these parameters to build models, so that we can then predict the behavior of MOSFET circuits or behavior of different MOSFETs with different mobilities or oxide capacitances, etc., by simply using these ideas. Okay. So, what I mean is you can extrapolate the behavior of other devices that you make after you have characterized your fabrication process flow. Okay. So, that is the whole point of parameter extraction. You can build compact models and you can predict the behavior of MOSFETs. So, what are the experiments? So, the very first one is what we will talk about is the IV and CV measurements, and I think this itself would be quite useful for most of you. So, you have made your MOSFET. Okay. So, we will just show 3 terminals, we will not worry about the body, and this analysis is true for any other kind of FET structure. We have not talked about say for example thin film transistors yet, we will cover that. But these ideas are valid for any other TFT structure, any of the MOSFETs as well. And the key experiments to perform, the very first set would be your IV and CV measurements. So, you have your MOSFET, you got a drain, source and gate. Now, we want to first do experiments to extract the transfer characteristics and the output characteristics, and then perform experiments to extract the CV characteristics of the MOSFET. Now, how do we do that? For transfer characteristics, we want to obtain a plot of IDS versus VGS, and this is done by setting the drain to source voltage to a certain value, and then connecting, you take the MOSFET to a probe station, you add in your probes. Okay. So, make sure that these probes are all connected to high impedance. You know, if you are going to measure voltages, they need to be connected to high impedance nodes, and we are going to measure currents, you want it to have low impedance. So, you typically want to be connecting these probes to a good semiconductor parameter extraction system, okay, or very good quality source measure units. And since we are going to be measuring very low currents in the MOSFET, you probably want to be using triaxial cables for current measurement. Okay. So, after making this connection, you want to be varying the gate to source voltage after setting for a certain drain to source voltage, and we will end up with a characteristic that looks like this. And then we would vary the drain to source voltage and again perform the same experiment so as to get another characteristic. And we can now obtain a family of curves for different drain to source voltages. So, this is the transfer characteristics. Now, you can take all this data and plot it on a log IDS versus VGS scale. So, you should end up with a bunch of curves that look like this. The next IV characteristics is the output characteristics, which is the IDS versus VDS curve. So, we would now take the MOSFET, set the VGS to some particular value, say greater than VT. We still do not know what VT is, but you set it to a particular value and we are going to vary that gate voltage. And you are going to sweep the drain to source voltage. So, when the drain to source voltage is swept, you now have a curve, a characteristics that looks like this. If the VGS is below VT, you will probably have a characteristics that does not show too much of current. And for larger gate voltages, we will obtain a family of curves which form the output characteristics of the MOSFET. Okay. And finally, we will perform a capacitance voltage measurement. Okay. And how do we do that? So, ideally we would like to do that on a MOS capacitor structure, that is a metal, insulator, semiconductor and back contact. But if we have a MOSFET, we make use of the overlap capacitances. So, you have a gate, you have the drain source, and we have a small overlap capacitance between the drain and source. So, if you consider this structure here, we have the gate, insulator. So, how do we perform the CV characteristics on a MOSFET? Now, ideally we would like to perform the CV characteristics using a metal insulator semiconductor architecture, but we can obtain such an architecture by simply short circuiting the drain and source, making sure that there is no current flowing, and then using the MOS capacitor in the semiconductor, in the MOSFET. So, at the end of it, we should obtain a family of curves that look like this. So, here I have not shown a family of curves, but we are seeing just one set of one data set. Okay. So, here we have the transfer characteristics. We have the transfer characteristics plotted on a log scale. Here we have the output characteristics, and here we have the CV characteristics of the MOSFET. So, how do we extract all the parameters required? By using this IV and CV measurement. Okay. So, the first point to note is let's write down our equations. These our theoretical models help us a long way. Okay. So, in deep linear mode operation. So, we have the MOSFET characteristics defined as mu Cox W over L. So, let me just make use of the entire slide here. So, we have the current voltage characteristics in linear operation to be mu Cox W over L into VGS minus VT minus VDS by 2 into VDS. Now, if VDS is made much smaller than VGS minus VT, then we can ignore this term and say that this is our current voltage characteristics. Now, the first thing you could do is once you have this characteristics, you could simply take all these data points, note the appropriate voltages, plug them into these curves and just solve those equations to obtain the unknown parameters. And what are the unknown parameters? The unknown parameters are the mobility, Cox and threshold voltage. VGS is known because we are applying the gate to source voltage. The aspect ratio is known because we have designed the MOSFET. Okay, so we know the channel width and we know the channel length. What remains to be, and VDS is known because we are performing the characteristics by setting it to a certain VDS. So, what remains is mu, Cox and VT, and we are going to use all these characteristics to define all these plots to define these terms, and we will use it to cross check and reconfirm these definitions. Now, as I said, you could take each point here and plug it into the equation and obtain the parameters. But then an easier way to do it is to perform the perform the IDS VGS characteristics at very low VDS and make use of this equation here. So, the slope at any point on this characteristics is simply mu Cox W over L into VDS. Okay. And if you were to extrapolate, if you were to take a tangent, if the VDS is really low, we will find that this characteristics is quite linear. You will not see too much of non-linearity there. If you take a tangent at say some point here, and why are we picking a point here? Because that is where VGS is the largest and that is where it is most likely that VDS by 2 is going to be much less than VGS minus VT. So, you take a tangent at that point and you extrapolate the tangent all the way to the x axis, okay, and the point at which it meets the x axis is a very likely value for the threshold voltage. Why is that? If you set your IDS as 0, you find that that can happen when your VGS is equal to VT. So, that is the x intercept. Okay. So, from this characteristics, what we can obtain is this product, which is mu into Cox and this value, which is a likely value for the threshold voltage. Now, what we need to identify mu and Cox separately is the CV characteristics of the MOSFET. So, let us now perform a CV characteristics of the MOSFET, and it could be low frequency or high frequency CV characteristics, it does not matter. But the point to note is, unlike in the case of a MOS capacitor, okay, the high frequency CV characteristics of a MOSFET will occur at a higher frequency. So, what I mean by that statement is that if let us take a CV characteristic of a MOS capacitor. Okay. So, we have the capacitance and voltage curve, and what we have done is we first performed a low frequency measurement and we obtained a characteristics that looks like this. So, let us say we performed another measurement, but it is at a higher frequency, and at some point let us say when the frequency was say 1 megahertz, we obtained the high frequency characteristics of a MOS capacitor. But it is very likely that if you were to take a MOSFET, okay, and perform the high frequency CV characteristics on the MOS capacitor in the MOSFET, it is very likely that at the 1 megahertz point that we still obtain the low frequency characteristics. And why is that? It is because the high frequency characteristics flattens out in this region simply because the electrons, the thermally generated electrons in the bulk are not able to respond to the change in the applied signal. The generation rate of electrons is not fast enough. And a MOS capacitor has to rely only on the thermal generation rate, because all the electrons are coming in only from this generation mechanism. But on the other hand, in the case of a MOSFET, the source can also inject electrons. So, you have the source and drain. The source is also, it is also possible for electrons from the source to enter the channel, and therefore, it is likely that these electrons will appear at the interface and on time, and that these electrons can respond to the applied AC signal. And therefore, it is possible that you still see a low frequency measurement in a MOSFET at the same frequency corresponding to a high frequency curve of a MOS capacitor. Okay. Nevertheless, so let us say we have a MOS capacitor or a MOSFET and we have performed the CV measurement. Okay. So, we end up with the CV characteristics that looks like this. Now, where do we obtain our information of Cox? Clearly, the Cox can be obtained in accumulation mode in this case. So, that is our Cox. Okay. Now, you should be very careful here, because the CV measurement as performed on a semiconductor parameter analyzer will give you the complete capacitance. Okay. It is the capacitance in farads. It is not Cox, it is not the capacitance per unit area. Okay. So, in order to obtain Cox, we need to take this capacitance and divide it by the area of the MOS capacitor used, and then we obtain Cox. So, in this case, let us say the MOS capacitor used had 100 microns by 100 micron lengths, and therefore, the area is 100 micron into 100 microns, which is 1e4 into 1e minus 8 centimeter square. Okay. And therefore, Cox in this case would be 20 picofarad, that is 1e minus 12 divided by 1e minus 4, which is about 1e minus 8 farads per centimeter square. That is about 10 nanofarads per centimeter square. So, that is the value of Cox in this example. So, we need to be careful with how we use the CV data. So, now we have Cox and we have the product of Cox into mu, and we can extract mu. So, just as a complete process, let's add numbers in a little later, but let us just go through the techniques first. Okay, so, we now know what is mu, we know what is Cox, and we know what is Vt, and all this has been obtained from these two characteristics. Now, what else can the CV characteristics tell you? Okay, the CV characteristic is a very powerful tool. It can be used to identify through a sequence of experiments. You can use it to identify trapped charges in the dielectric. Okay, we will talk about an example of that in the next slide. You can use it to identify Cox. Okay, but you can also use it to identify the typical flat band voltage. So, we know that the flat band voltage is in and around this point here. Okay. And it is also used to identify the semiconductor capacitance. Okay. And what do we mean by that? So, this is the depletion and the interfacial capacitances combined. Okay. And how do we do that? At the high frequency characteristics here, we know that this is a series combination of Cox and the semiconductor capacitance, and that is basically the capacitance here, which is 10 picofarad, okay, divided by the area, okay, is, and we said let us say it is a 100 micron by 100 micron device. So, this divided by your 1e minus 4, 1e minus 8 is nothing but 1e minus 4 is nothing but the series combination of Cox and Cs. And what is Cs? Cs is nothing but your depletion capacitance plus interfacial trap capacitance. And if interfacial trap capacitance does not exist, then it is purely your depletion capacitance. Okay. So, at in the high frequency characteristics, it is very likely that the interfacial trap capacitances will, the interfacial trap charge will not respond, and therefore, it is very likely that this is simply the depletion capacitance. And if we know the depletion capacitance, we essentially know we essentially know epsilon s by xd. So, that is the depletion capacitance per unit area. And if epsilon s is known, we essentially know xd, which is the depletion width in the semiconductor. And since depletion width depends upon 2 phi f and among several other parameters, we actually know the doping concentration of the semiconductor. So, CV characteristic is quite a powerful tool. You can make very good estimates of all these parameters. Right. So, now we have obtained Vt, mu and Cox, and we can now plot the same transfer characteristics on a log ID versus Vg scale in order to look at the subthreshold behavior of the MOSFET. So, we know Vt. So, we know that in and around let us say about 2 volts, okay. So, after 2 volts the MOSFET enters above threshold operation. So, here it is all given by a square law characteristics, and below this we know that we are in subthreshold region. So, here you can see that even though there are few data points, it is an almost linear dependence, and we can now calculate the subthreshold swing of the MOSFET, the subthreshold swing of the MOSFET. And what is the subthreshold swing? It is the volts per decade. So, how many volts did it require? What was the gate voltage required for the MOSFET to travel 1 decade up in current? Okay, so, this is 2 decades up in current, and the gate voltage required there is about okay, we do not have a gate voltage scale, we have a scale here. So, the gate voltage required is about 1 volt for the current to travel up 2 decades, and therefore, it is 1 volt divided by 2, which is 0.5 volts per decade as the subthreshold swing. Okay. So, that is how you calculate the subthreshold swing. And subthreshold swing is also related to 1 plus C depletion by Cox. And if there is no interface state capacitance, we can calculate C depletion here, and we can cross check with the C depletion extracted from this place. And if there is a mismatch, it is possible that you have interfacial trap capacitance, and therefore, it is also an indicator for, it is also a means to combine these 2 characteristics to extract the interfacial state capacitance, because the interfacial trap capacitance will not respond at high frequencies. It is less likely to respond at high frequencies. So, this is one useful parameter you can get from the log ID versus VGS characteristics. And the other useful parameter is, since you are looking at the log scale, it is possible to identify the leakage current. And by plotting a family of curves at different VDS, here we can identify the gate induced drain leakage, drain induced barrier lowering, and these phenomena. Okay, you can identify the different leakage mechanisms, and we know the impact of VDS on leakage, and it becomes a very useful tool to study the mechanism of leakage. So, we know the leakage current. So, in this case for this one characteristics it is difficult to identify the mechanism, but we can say that the leakage current is 1 nanoamps. So, that is the leakage current through the MOSFET. So, this is when the MOSFET is supposed to be off and yet it is having a current that is not 0 and that leakage is 1 nanoamps. Okay. So, now finally we will plot the output characteristics. So, since we already know mu, Cox and Vt, we can cross check to see whether the output characteristics in linear mode matches the use of these parameters, and you can iterate between all these plots in order to see whether we have the right parameter set. But in saturation mode we observe for two other features. Okay. The saturation characteristics, I mean the output characteristics is quite powerful for a circuit designer. So, in saturation mode we firstly identify the point at which saturation occurred. Okay. So, technically this should be VGS minus VT, but it could be offset by some amount because if you remember the bulk charge theory predicts a different saturation voltage as compared to your square law, the simple model. So, this could give you indicators as to those corrections involved, and it is also a cross check between this Vt and the Vt obtained in the transfer characteristics, because it is only at VGS minus Vt that you enter saturation. The next point is to look at the variation in current due to VDS in saturation. Okay. Now, this variation in current due to VDS is theoretically not supposed to exist in an ideal MOSFET. In an ideal MOSFET the current is supposed to be constant with VDS, but it is because of channel length modulation that you actually have a variation in current in the MOSFET, and therefore, this is a useful plot to identify your channel length modulation parameter and the effective output resistance of the MOSFET. Okay. So, what do you mean by the output resistance of a MOSFET? It is a output small signal resistance of a MOSFET, which means that if I were to fluctuate, if I were to set this as my DC operating point and if I were to fluctuate VDS around this point, what is the fluctuation in the current, and that slope or the inverse slope of that tells you the output impedance of the MOSFET, which is to say that if you have an ideal MOSFET with no channel length modulation, in saturation operation there is supposed to be no current in this MOSFET, but we then use this ideal MOSFET and we then add a parallel resistor, a resistor in parallel, so that when the MOSFET operates in saturation the current here is 0, the small signal current is 0, whereas the small signal current in the resistor here is not 0, and it is in fact defined by the current variation in saturation mode. Okay. So, just as an example, so since we have already performed a few calculations, just as an example, if you have to run through these numbers a bit, let us just quickly do that. So, these are very powerful experimental techniques to extract all these parameters. So, let us just run through it and throw in a few numbers in place. Okay. So, this is quite important from the point of view of example problems or your assignments, because you will be given assignments with regards to these kind of parameter extracting parameters. So, firstly let us say we performed the MOS capacitances on MOS capacitor having 100 microns by 100 micron. Those are the dimensions, which means that was 100 microns, that was 100 microns, and that was the MOS capacitor that we used. Okay, so that is a metal, insulator, semiconductor, back contact. So, what is 100 microns by 100 microns? We would like to represent everything in terms of centimeters square. So, what is 100 microns into 100 microns? It is 1e4 into 1e minus 8 centimeters square, which is about 1e minus 4 centimeter, sorry 1 centimeter square. Okay. And the capacitance, actually the total capacitance measured here, that is the Cox in accumulation mode, is 20 picofarad. So this is all in picofarads, that is basically your 20 e minus 12 farads. So therefore my Cox is essentially this capacitance divided by the area, which is 20 e minus 12 divided by 1 e minus 4, which is 20 e minus 8 farads per centimeter square. Okay. And the capacitance here, that is basically your Cs in parallel with C depletion, is much lower. It is of the order of 10 or maybe less than that, it is about 8 picofarads, and therefore my Cox in series with C depletion is 8 picofarad by 1 e minus 4, which is about 8 e minus 8 farads per centimeter square. It is about 80 nanofarads per centimeter square. Okay. So do forgive me if I am making typos here, but I think it is right. So this is about 200 nanofarads. So I think when we had the discussion on CV measurement earlier, I made a mistake. It was one order lesser, but what this tells you is Cox is 200 nanofarad per centimeter square. So now let us come to the slope. So what is the slope here? So let us say this point here is about 1.5 e minus 4, that is the current, that is at 10 volts, and we will go a long way because it is quite linear, these are quite linear characteristics, and let us say this was all plotted at VDS is equal to 1 volt. So over here we have a VGS of 5, here we have a VGS of 10, and here the current is about 5 e minus 5, okay, or let us say 0.5 e minus 4. So the slope, that is your d delta ID by delta Vg, okay, is essentially 1.5 minus 0.5, which is 1.0 e minus 4 divided by this voltage difference, which is 5 volts. So this slope is about 2 e minus 3, okay, and that is supposed to be our mu Cox W over L into VDS. So let us say VDS is 1 volt, so that is 1 volt. Let us say the aspect ratio is also 1, that means the channel width is equal to the channel length. Okay. Now we know Cox is 200 nanofarad per centimeter square, 200 e minus 9 per centimeter square, and that is all, and that into mu is equal to 2 e minus 3, which implies that is going to be E6 and that is going to be E4, okay, which if I have not made a mistake here says that the mobility is quite high, it is in fact dramatically high, okay, and it is about 10,000 centimeter square per volt second. I am quite sure I have made a mistake here, but nevertheless that is the way you go about calculating this. Okay, so let us just cross check this, 1 e minus 4 by 5 volts, that is 10 e minus 3 by 5, which is 2 e minus 3, and the capacitance was 200 nanofarad per centimeter square. Okay, so since we have made an assumption on the aspect ratio let us say is 10, and let us say the VDS is 1 volt, okay, and let us say we do not know mu, and therefore this slope must be equal to this number, okay. So which means that 6 and your mobility will be about 1000 centimeter square per volt second. Okay, so yes, the numbers do not make complete physical sense because we are just arbitrarily picking up VDS and aspect ratio. So, there is no typo, it is just a mobility of 1000 centimeter square per volt second is more acceptable considering the fact that we are using silicon as our role model. Okay. So, these curves are by no means actual data sets, they are just plots prepared on an Excel file using the parameters, using a certain number of parameters and using these models. Okay, but it is just for the sake of this exercise. And then let's look at the log ID versus log VGS characteristics. We have already looked at this. So, we saw that the subthreshold swing is in order to get this past 2 decades you need about 1 volt, and therefore, it is about 0.5 volts per decade. So, that is the swing. And let us look at the output resistance of the MOSFET. So, here we can see that the small signal output resistance, the Dow VDS by Dow IDS is you can calculate that quite easily. So, let us just mark 2 points. Let us say that we keep one point here at 0.0015 and the next point here which is actually okay and the next point here which is close to the edge which is say 0.0018, which means the difference is about 0.0003. Okay, so the difference in the currents is the order of 3 minus 5. So, that is the delta I, and that happens for a voltage difference of about 3 volts. Okay. So, that's quite a large output resistance, but not large enough. So, it is about 100 kilo ohms. Okay. So, this is the way you go about extracting parameters. Okay. If I made a mistake in these calculations that I am doing here, I do apologize, but you have the idea, you know what has to be done. So, this is a very powerful tool to extract parameters.